Hi, I'm Chris Brown, and this is the sixth of the second section on, and this should read intermediate level axiomatic design. So section 2.6, kinds of coupling. So the objective here is to achieve better recognition of coupling by categorization types. So again, looking for categories so we understand how to treat things. And we want to devise approaches to address the coupling based on the categories. Rationale. Application of Axiom 1 requires that a coupling which eliminates independence is identified. And there are several kinds of coupling. And we're going to look at, conventionally we look at the FRDP matrix, and then we can make up a special kind of matrix here and say, all right, well, we've got FR-FR coupling. We could have FR-DP coupling and DP-DP coupling. Since FR-DP and DP-FR coupling are essentially the same, this gives us three kinds of coupling that we might want to look at. Now, this one is the one, DP-FR, that we've been looking at mostly so far. And then another kind called sequential coupling. So what happens now if we look in the FR space, and let's just consider two FRs because it's easier to draw, and we have one solution, then we'd like to move to a second solution. So we need to know what sort of functions the FRs are the DPs in order to adjust the functions in order to meet a certain solution. So we need to know how the DPs and the FRs map onto each other. Now the best is where the axes are parallel to each other, and this is going to result in FR1 being a function only of DP1 and FR2 being a function of only DP2, and then this will lead to a diagonal matrix and a completely independent design, and so the DPs are orthogonal and parallel, are orthogonal to each other and parallel to the FR. So this is the best solution. Now this does not address design when we're looking at physical integration or processing, and those will be addressed later. So here's the diagonal matrix that results when the axes are aligned this way. Now suppose that we've got non-orthogonal FR axes. Then we have FR-FR coupling, and we end up with a full matrix that's completely coupled. And this means that FR1 is some function of FR2 as I move along, and so they are not orthogonal. So it doesn't matter what DPs we have. We cannot decouple this this design, and it needs new FRs that are in fact orthogonal. So the FR-FR coupling, when we look at the design matrix, this results in a coupled design since one FR influences the other, and this needs to trigger a return to the FR selection. So here's what the matrix will always look like when you have FRs and DPs that are coupled. So FR-FR coupling while developing FRs, this needs to be identified. It should be identified by it not being mutually exclusive before the DPs are selected, and this should result in developing FRs that are mutually exclusive. And so we would need to make one or both of these coupled FRs a constraint. That might be another approach. Here's how we end up with a triangular matrix in this kind of embodiment. And so the DPs may not be orthogonal, and one may not be parallel to the FR matrix. So in this case, FR1 is a function of both DPs, because motion along either of the DP axes results in a change of FR1. And FR2 is only a function of DP2. So the DPs are not orthogonal, and one is parallel to one of the FRs, and the other is parallel to neither. So any adjustment in FR2 by changing DP2 will result in a change in FR1 and require a change in DP1 to adjust FR1. And so this is a triangular matrix, right? This is going to result in a triangular matrix. So here's another situation, and so the FRs might be orthogonal, but both are inclined to the FR axes, and so then we have another fully coupled situation, but at least one of these DPs needs to be changed then when we're in this situation, because that will also result in a fully coupled design matrix. Another kind of coupling that we should look at is the integrational coupling, DPs on DPs. So when we do the decomposition and bring it down to the leaf level, we essentially have all the components, but nothing's physically integrated yet. And in the first section on this, we talked about physical integration. And so and so we don't want to introduce coupling during the physical integration. So there's a corollary in axiomatic design about the integration of physical parts. And they should be integrated into a single part if the FRs can be independently satisfied in the proposed solution. Let's consider this for a moment, because one of the dictums that's often given to designers is to reduce the number of parts. And this is a good idea as long as it does not result in coupling. So have just as few parts as you can, but no fewer. And so we need to make sure that when we reduce the number of parts, the FRs are still independently satisfied. So physically integrated, functionally decoupled. So that comes from the book on axiomatic design. Now, here's an example of DP-DP coupling. This comes from the dashboard of an older model Subaru. And so we have coupling between the cup holder, as we can see, and the controls for the air conditioning system, and access to the tape deck and radio. So you have some idea about how old this is, because hardly anybody uses this kind of tape anymore. But it's a good example, though, because there's no physical reason, there's no law in physics why cup holders interfere with the controls for the air conditioning and the ventilation, or why it should interfere with the radio. And it's only through the integration of these things that that occurs. So you can look at a DP-DP matrix. Now, certain things need to be adjacent to each other to work. The wheels need to be near the axle and so forth. But there's no reason why the cup holder, DP1, should be interfering with the radio or the ventilation controls. So if you look at a matrix like this, and you can identify which things need to be physically integrated and which need to be separate. So functional independence does not require physical separation. So axiom 1 refers to functional independence. And physical components fulfilling separate functions do not have to be physically separate. And in one of Sue's books, he looks at a beverage can and identifies 12 different functions, but they're all physically integrated under one beverage can. All right, so that's FR, FRDP, and DP-DP coupling. Let's look at sequential coupling, and this comes up in manufacturing. So when we have one task that has to be done in sequence with a previous task, then you can have some kind of sequential coupling. So the probability of being successful in the second task is conditional on success in the first task. Planning is one situation where you can see this, besides manufacturing. Also in design work, what do we design first? But it's also quite clear in production lines, and can be important in computational algorithms. So sequential coupling solution. One is, how do you address this? Well, use constraints, so that on exiting each station in a sequence of operations, the output is must meet certain criteria. And then and then the stations can be designed independently once that constraint is understood. Another is to decouple by inspection. So here you need an additional FRDP pair. And so this is kind of captured in Jay Black's dictum for manufacturing: make one, check one, move one on. So you don't move it on until you're sure that it has been successful. So that's a way of kind of decoupling this. So you can try some kind of fault-tolerant design and decouple them, or design an interface that helps to uncouple the stations. So if we have part flow coupling only, each station must meet interface constraints that the output of one is the input to the next. And they can be designed independently once that constraint is understood. And this is a constraint, and the stations are not essentially coupled when we look at it, when we do it this way. So the elements of each station depend on each other in that changing the design of one changes the other. But the elements cannot be designed independently. So we want to avoid this or reduce the degree of coupling through good design choices. And sometimes we do need to do this in order to achieve tight tolerances. In other words, we need to measure the part and make some adjustment in the next process before we can go ahead. But sometimes there are creative solutions. So suppose you've got a drilling, tapping, screwing operation. And so if I haven't drilled the hole in the right place, I can't tap it in the right place, and obviously then I can't screw it in properly. So how can we do this? So are these necessarily sequentially coupled? That's an important point. And so what if we take a look at this kind of fastener that actually has a drill and a tapping portion incorporated into the threaded fastener. So these are physically integrated and functionally decoupled. And it's one way of solving the sequential problem, is to integrate the sequences on some kind of tool or shaft or part, so that they are all happening sequentially but not requiring another operation. Here's another example, designing the planning process for facility parking. So if we have to plan the parking and plan the scheduling, are these two separate planning groups? Do they need to interact? On the first day of a new hospital operation in Hanover, New Hampshire, the second shift arrived and there was no place to park because the parking people had only planned for one shift at a time. So the planners, so there was a need for the scheduling and the planners to interact. The way they scheduled, they really needed twice the amount of parking that they had. Thank you for your attention.